In this video, we'll get back to coding our design, adding the power management circuits that translate 24 volts in to the 5 volt, 3.3 volt, and 1.2 volt rails. We'll practice the skills of pulling in code from libraries and wiring circuits using ports, using parametric functions that automate detailed regulator design, and we'll also go through the automated layout tools for creating power geometry and optimizing power layouts. First, let's make a new file for holding the power management circuitry. Open up controller.stanza, save it as power.stanza. We'll change this to power and change the module to power management. We can clear out the FTDI and let's get our ports. So we'll have a VDD 3v3 rail. We'll have VDD USB, and we'll also have a VDD 1v2 rail. Let's construct the power circuit, and we'll start with the 24 volt to 5 volt regulator. Through awesome JITX, we can find TIVreg, which is a library for automating circuits around Texas Instruments voltage regulators. For our 24 volt circuit, we'll use the TPS 6293, which has a up to 30 volt input range. So let's go ahead and copy the application circuit code and add it to our design. Here we have code that sets up the buck regulator design problem. You have high level specs in, like voltage input, voltage output, your target ripples for input and output ripple, the output current, frequency, and K factor. And here you have the configurations for this specific circuit, like what's our frequency, what's our soft start period, what's our undervoltage lockout parameters. So high level specs, and then the circuitry inside here is going to do all of the detailed design for us. So let's just put in our set point. We're going to correct this to, say, variations between 20 and 28 volts. And I'll change the voltage output to 5.5 because with that diode bridge to USB, I want to make sure that if 24 volts is supplied, that supply will be used. Let's also add the regulators for the 3.3 volt and 1.2 volt rails while we're at it. We'll use the 6208 for those rails. And again, let's copy the application circuit. Here's 3.3 volts. Voltage ranges up to 5.5. And we can change this code to 1.2 volts. 1v2. And we'll want to change the voltage output to 1.2. This rail can accept 5% tolerance, and the rest of that looks pretty good. Okay, so we have 3 regulators configured here. Let's just quickly finish up the code to connect them. We want a diode-OR for the 5 volt rail from the regulator and the V-bus line from USB. So this is a simple circuit. You could easily add the components and write out the nets, but it's faster and less error prone to use parametric circuits. So if we look at the power systems library, we have a diode-OR function. Pass it which diode you want and how many inputs you want. So we'll have 2 inputs for our design. And the nice thing about using a library circuit is that you have nice ports on it. So we have a port VIN, which is of type power by the number of inputs. So we'll have 2 power ports and 1 VOUT port. So we'll say net, the USB OR, which we need to change here, USB OR dot VIN, say 0, and we'll use VDD USB for that. Again, we're connecting a power bundle to a power bundle. Everything else under there is handled. And we'll connect this input to the output of the DC-DC 5 volt regulator. So this is DC-DC 5 volts, and the bundle there, com.v, that's the output bundle. And then we need to connect the output of the diode-OR, USB OR.vout to the DC-DC 3v3.vin, and we'll want the 1.2 volt as well. And finally, we can wire up the rest of the ports here to say that we have, well, we want to connect the output voltage of these two ports, V out to VDD 3V3 and 1.2 to 1.2. Okay, so connecting the output of those regulators to the ports on our module. So you want to use code that reflects your design intent, so the code that you write should look pretty cleanly like your requirements. We're going to use the 1.2 volts for the core on the Ethernet switch, and so that needs to come up before the 3.3 volts. 1.2 volts. So just like you might leave a comment in a schematic, except this is much more tied to like the functional goal. So we'll say we'll want to connect the enable pin of the 1.2 volt regulator to the positive output of the USB diode-OR, diode.V plus, 1.2 volt enabled immediately, and then we then connect the power good pin, DC V2.power good, to the enable pin of the 3.3 volt regulator. So once that's stabilized, 3.3 volts gets enabled, and we'll also want a pull-up resistor. So we'll use that input, this insert pull-up function, which is very handy. So we say, what pin do we want to pull up? So the input to this board is going to be a 24 volt daisy chain. Let's go to our connectors library, and we'll use the Weidmuller terminal block here. So this is a parametric series of devices. We'll want the 4-pole version. And finally, let's add the nuts to hook that up. So got named net P24 volts. We'll connect that to the first 2 pins of the terminal block. I think that's right. Yeah, port P and P2. And that is also connected to the 5.5 volt V plus. And similarly, we'll want ground to be on 3 and 4, V minus. And we'll also want to pull in the overall ground, which I think we can access on any ground pin. Let's call it V minus there. Just make sure the connection is made. That's ground. Okay, so let's save that. In main, we can import power. We'll add a common port for the 3.3 volt rail. And here we can instantiate the power management. So power. And then we can make a few more nets to wire up the interfaces. So we'll say net VDD 3v3. That can connect to rail 3v3 as well as the controller 3 volt. And we'll also connect up the VDD. To install the SLM files here. So let's install power systems, copy, paste, and TIV reg. Copy, paste. Power control. There we go. Fix a couple typos. Now there's going to be quite a bit of design work that happens behind the scenes. From the high-level specifications of the buck regulator code, it is going to be designing input and output filters, choosing inductors, choosing capacitors, choosing resistors to create the feedback network. So that voltage divider solver is another parametric circuit that you can call. And it's going to guarantee that under all variations of manufacturer tolerance and thermal variation with the TCR of the component, that this output is going to be achieved, and making sure that those values are triply sourceable as well. And the nice part about that is that it's a solver you can write once and just reuse. Okay, so now we have quite a bit of circuitry. 3 different regulators, a diode-OR for the power combination, and our input connector. For the next step, I'll be completing the layout, and we'll switch to the pop-out views in the schematic and board. I like to use the schematic and the board when I'm doing power regulators, so let's go ahead and clean up the schematic. I'll start with the 24 volt. I press U here, U again to make sure that it's all selected. Shift double click. We have it cross-selected in the schematic. I'm also going to move these for grouping later. So in the schematic, we'll grab all of these different schematic blocks. You can see each one of these was a little solver that came in. Solver for the input regulators, the output capacitors and filter, and the voltage divider network. We'd like to have those in one group. And then, so Q to link, L to relayout. We've got a starting layout for that, and we'll repeat that for the other regulators here. Okay, we have and the power connector. I'll just roughly organize these, because this tutorial is about layout. So we can move our power connector roughly into place. Let's say it's there. Get our diode bridge roughly near the USB. I don't need these components right now. And let's start with the 24 volt regulator. So we have our, we'll grab the input capacitors, which will be here. And let's bring those down near the 24 volt net. Now, to start creating power layouts in JITX, remember how when everything's auto-routed, you can move things around and everything updates. We want to keep the same thing for power, because what you're going to want to do is optimize the layout of your regulator to get low resistance planes, minimal capacitance, really try to up the performance and density. So we do that by creating pore regions that are also automatically generated. So highlight the pads that you like to contain and press C. And that creates a pore on the selected layer, which was our top copper. So now you can see as I move these capacitors around, the geometry is just going to update. And you can combine this to make general high performance layouts. So if you auto via twice, let's say that we want to, let's have our vias there. About that pitch. And again, you can select all this and press C to create a containing region. So now you have easily generated pore regions for power geometry. Okay, next we'll bring in here's the controller. And let's convert that with a trace. And for power, you can use adaptive traces if you like, which will create a thicker region for lower inductance and resistance routing. Okay. And I don't necessarily know the entire flow of my power layout, So I'm just getting this sketched up to see what it is going to be. So I kind of discover that through the layout process because I want a high performance layout for this thing. So let's get all of the parts in order to do that. Okay, here we've got our configuration passives. Let's create a little more room here. Okay, we got our output capacitors. As before, we can press B to align to first, distribute B. Okay, looking pretty good. And we'll create a region off of that. Okay, don't necessarily like the size of that, but let's see what our overall flow is going to be first. We've got this boost network here. Route all that out there. We've got our, this would be the, what do we got here? This is a DNP capacitor on the, looks like the feedback network. Yes. Okay, schematic layout. Didn't do a great job there, but yeah, this is our feedback network. So we get that into place as well. There's a better layout possible here. Okay, we need a route. Oops. Get a route going that way. Again, definitely not perfect. We're just roughing this out right now. And here's our soft start capacitor. Make some room for that. Okay. Any other parts we missed? Yeah, all right, we've got our undervoltage lockout divider here. Ground, get a via, on this pads, and we're going here with it. So let me move this per head. Okay, so rough layout for this device. I'm going to finalize this when we add the rest of the regulators, because this is supplying those other regulators through the diode bridge. So for example, maybe I want to swing this around over here and keep that short to minimize stray capacitance. That's looking pretty good. And this output, I don't need that, but I'll create another region here, just with C, to feed the diode bridge. And what else? Do I like this input here? Actually, I might rotate this power connector around, get a bit denser layout. Yeah, that looks better. I can offset this as well. So I could expand this pore. You can just open it with the edit menu. Say give it another 0.5 millimeter. And while we're at it, we should demonstrate that The pore creation tool is actually a region creation tool, and you can do it on any layer. Select these pads first, then select the layers I want. So I'm going to select those layers, deselect copper, and press Shift-C, which creates a region with an automatic offset. Give it, say, a 0.5 millimeter of clearance. And you can see those keepouts were created on that layer, on those layers. Okay, moving on, let's get our other power regulators going. So maybe I'll get this diode moved up here, this whole thing over this way, and let's connect the V bus. So if you press A, it selects every pad on the net. So I'm going to do one thing. Manual routing mode with Shift Q, hold down 2 to press a control point, and you can add this to your region. So I'm just going to resize this to 1 millimeter, and you've got a nice little connection point that you can use. Press A, Control Shift Select, press C. And now you have a local power pore for the bus that includes this control point, and I can use that to route to these traces, for example, and I can increase that trace size to, let's say, 1 millimeter, and give it a 0.2 clearance. And you still have this sort of alive aspect to your layout where we can figure out what our ideal configurations are. Okay, speaking of, let's get these other regulators figured out. I'll bring my inductor in here, C to create a region, C to create a region. Input capacitor, you can identify with the short trace there. You could route it, and you could also press C. So as a backup, nothing's stopping you from creating additional pores. Auto vias for ground fan out. And let's get all those in a ground region. Why not? All right. We've got this resistor here. Here are our output caps for this device. Again, region. And this would be our feedback network. Right? Yes. Okay. Ground via, select and route, and I'll route with a trace to the output of this. Speaking of, I guess we can create some vias. So I'll delete this region and say add some vias to it. Let's get 4, and these can just be roughly in place. And then recreate the region that includes all of these for the output as well. Auto via there, and another region. Notice that these regions have started interacting because they share each other's space. So I can go here and select the priority and up the rank on that pore such that it correctly fills the space. Right. I'll just route there for the time being, and route that. Okay, so that looks like a reasonable layout for this regulator. And the input is going to be from the diode bridge. Okay, interesting. Let's try it here. And then we'll give this other regulator the same treatment. We have some layout reuse to demonstrate, but for showing the power regulator layout, let me just re-demonstrate everything. So, inductor into place. Press C to create regions. Move this there. Actually, I can move this a bit closer as well. Huh? Input capacitors. Feedback network. Auto via to fan out. Route. Now I can hold Q and 1 to drag out vias. And if you hold Control, you get straight line locks as well. So if you wanted to create a grid of or regularly placed vias, you can do that. So we'll create the output region, route to our feedback network, vias to ground, create a region. Looks good. Input capacitor. And we'll create a local ground pour. Oh, that was via mode. C. Okay, and here we have the, this is the enable resistor. Okay, so we can move this over here. There's our enable. And it also has a pull up to V in, so maybe I'll move that down here. Okay. Alright, so there's our second regulator. And we'll put a control point here. So we hit the middle of this inductor, which I don't really like routing under. And that's looking pretty good. Okay, so how's our flow looking? So we have our voltage input here. I could probably move this connector over to get some clearance from the corner. I think this is looking pretty good overall. So we're going to want to route the output here to these inputs. And to do that, let's do one more thing. So let's create a region. So you can modify this region by pressing M. And you can drag the points to where you want them. Like so. So our power region comes out to there. Let's do it that way. You can hold Shift to add a point and then drag it into place. So holding Shift here to set up our regions. I like not having sharp internal corners. And it's looking pretty good. And we can bring it down like that. I think we all like straight regions on circuit boards there. Okay. That's looking pretty good. Hit enter to exit. And now we have our modified region here. So I'm going to add one more point there just to make it nice. Okay, so that looks pretty good. Notice that we've got some issues with poor priorities here. So again, increase the priority of this from the default of 20, such that it takes priority over overlapping pores. Okay, these need outputs. Again, make another little region there. And because it's overlapping, increase the priority. One thing to note about this pour is that once it's edited, it no longer updates live. So these we haven't edited and it's just auto-generated. The new shape can be calculated automatically. Once you edit a pour, it is no longer auto-updating. So just one thing to be aware of there. Let me show you one more method of creating power pours to finish up. So our FTDI chip has a internal 1.8 volt regulator. which has these components on it. So you can create a region here. And we kind of want this like interesting C shape. So let's go to M to modify. And we can change this from the traditional mode where you drag points around to Sculpt mode. And there you get more of a freeform drawing tool where you get to come in and sort of sketch out the flow that you want for the region. So it's quite a powerful tool. You can hold different keys to nudge versus shove and simplify. And you can also turn off, extract the boundary, hold control, and it does a smoothing operation. So a bit more of a freeform tool for editing your zones. So great for if you want to quickly sketch out a region and see what it looks like. You can use that sculpting mode. So again, to modify, press S, and then I want this inside corner as well. And no sharp internals. Okay, and there's our 1.8 volt power plane. This video showed how to create power circuits using parametric code, and then how to use the auto-routing features in JITX to lay out your power regulators, creating pores, adaptive traces, and then customizing those regions. Our next video is going to focus on high-speed design and auto-routing the gigabit Ethernet interface.